All right, the third and final property of the mean that we're going to look at is this one. And it says that the sum of, right, remember that, sum of, all the x minus x bar squared is always least. All right, so another way of saying this, the sum of all the squared deviation scores is always least. Now, I'm going to explain it, and then we'll talk about why we care. All right, talking about why we care, let me just say a couple things about why we care about the first two properties of the mean. Remember, the first property of the mean was that x bar is a consistent estimate? Well, that means, just to refresh, it means that as we increase the sample size, x bar gets closer and closer to mu. In other words, we're going to get better and better estimates. All we have to do, in theory, is increase our sample size. Why is that good? Well, because researchers like predictability. We like knowing the fact that if we want better estimates, we just have to increase our sample size. Okay, so it's that predictability that we like. The second property was that x bar is the center of gravity for a set of scores, and I helped you to understand that. So the reason why we like that is just because it helps us to understand what x bar is doing and why we should consider it to be representative. Don't you think being the center of gravity would be a good way to say that's a representative number? I mean, I do. If it's the center of gravity, I would think that, yeah, I'm completely balanced. I'm representative. So that's why we like that one. But what about this one? Well, let's define it, and then I'll tell you, I'll give you some idea of why we care. Okay, so what it's saying is for a given data set, so you have a sample, the sum of all the squared deviation scores, remember x minus x bar is a deviation score, so if we square them and add them all up, that number will be as small as it can get. But that's only true as long as you use the mean in your calculation. If you substitute any other number, the answer will be larger. So let me explain what that means. Okay, now we're going to have to take this column by column. So here were all your x bars, your x's, right? Your scores. They were 1, 2, 3, 4, 8, and 9. Those were the scores in the sample. And then remember that we have to subtract x bar, right? Because that's what it says here, x minus x bar. So x bar was 4.5, so we're going to subtract 4.5 from all the raw scores. And here's our answer, negative 3.5, negative 2.5, etc. These are all the answers. But this says what we have to do is we have to square each and every one of them. That's why there's a little 2 here beside each answer. So we found what x minus x bar was. Now we have to square it, right? So when you square x minus x bar, here are the answers. So if we do minus 3.5 squared, we get 12.25. Minus 2.5 squared is 6.25. All right, and I did that for everything, everything else in this column. All right. Remember, when you take a negative and you multiply by another negative, you always get a positive answer. All right. Now we have to add them all up, right? Because it says sum them. So we did all the x minus x bars. Then we squared them. The next step is to sum them. So here is the sum. If we added all these up, we'd get 53.5. Now, what this is telling us is that as long as we use 4.5, right, 4.5 here, that's the mean. As long as we use that in our calculation, there's no way possible we're going to get a smaller answer here. This is as small as it can get. Now, some of you are saying, I don't believe that. Some of you might be curious or saying, why don't you plug 0 in? Instead of using 4.5, which was the mean, what happens if you put 0 here? Well, let's try it. All right, so the first step is to find out all the x minus x bars, right? That's step 1. So we're going to do x minus x bar x minus the mean, etc. So this calculation was really easy because 1 minus 0, of course, is 1. 2 minus 0 is 2, etc. So these are all the x minus x bars. But you have to take each one and square it. So we're going to have to take our x minus x bar and square it. 1 times 1 is 1. Do the same thing here. 2 squared. So 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 8 times 8 is 64. 9 times 9 is 81. Now the last part says to add them all up. So we have to add up all these answers, and we get 175. See, this is a larger number because instead of using the mean, 4.5, we used 0. Now, somebody could say, well, what if you put in a negative number? Or what if you did this? Or what if you did that? And my answer is going to be, it doesn't matter what number you put here. As if you put 4.5, you're going to get the smallest sum that you possibly can get. Any other number, other than the true x bar, any other number is going to give you a larger sum. Now, obviously, I can't plug in all the different possible numbers in the world and beyond because we would never, well, we would die before we could complete that. There is a mathematical proof for this, but I have long since forgotten what the mathematical proof was. So if you want the mathematical proof, you'll have to go to the math department and ask them for it, okay? Now, more importantly, why do we care about this? Good question. Here's why we care. It will help us minimize error, both in inferential tests and in something called regression. Now, it is too soon in the course to explain how this little thing up here is going to help us minimize error in our calculations. It's too soon because you haven't learned about the inferential tests specifically yet. You haven't learned about regression, so it's too soon. I can't do it. Remember, you can't read Shakespeare until you know what sound the letters make, etc. But we will get to it, all right? And then we're going to get to it towards the end of the course, and then I'm going to talk about this again, and hopefully you're going to have I get it now, right? But now you just have to trust me, all right? It's going to minimize error in many different ways. That's why we care about it.